Hello, in this video I am going to solve question 3 from problem set 1. Let us read the question together first. Is the function capital F defined on R, the set of real numbers, by capital F of x equals to x squared times sine of 1 over x if x is not equal to 0, and 0 if x is equal to 0, an antiderivative of the function little f defined on the set of real numbers R by little f of x equals to 2x sine of 1 over x minus cosine of 1 over x if x is not equal to 0, and 0 if x is equal to 0. Motivate your answer. The short answer, of course, is yes. In this case, capital F is indeed an antiderivative of this, is an antiderivative of function little f, but let us show that. Okay, so I need to prove this. I need to prove that for all x in R, f prime of x exists and f prime of that x is equal to little f of the same x. So this is what I want to prove. Okay, so we say that if x is not equal to 0, then what happens is that the function capital F of x follows the first rule, that is x squared sine of 1 over x. So in that case, if I differentiate it, this function f, capital F, is differentiable if x is not equal to 0 because this function f is a product of two functions, and each one of these functions are differentiable if x is not 0. So it means that the product is also differentiable. And to differentiate it, I have to use the product rule. So it becomes the derivative of the first function multiplied by the second function itself plus the first function x squared multiplied by the derivative of the second function. Okay, and if I continue, the derivative of x squared is just simply 2x multiplied by sine of 1 over x. Then I have plus x squared. Now if I want to differentiate this part, I need to use this rule. So we know that cosine of u, we know that the sine of u, where u is a function of x, is differentiable if u itself is differentiable, and the answer is just simply cosine of u multiplied by u prime by the chain rule. So I give the role of u to 1 over x and use the same formula. So this becomes multiplied by, so let me change my color, multiplied by cosine of u, which in this case is 1 over x, but multiplied by 1 over x prime. Okay, but it is simple to see what is the derivative of this one. 1 over x prime is x to the power, yes, so you can write 1 over x, so that 1 over x prime is equal to minus 1 over x squared. So that's very simple to realize. So this becomes 2x, and then I have sine 1 over x plus x squared multiplied by cosine of 1 over x multiplied by minus 1 over x squared. And then now you see that this x squared here and that x squared there are cancelled, and this is negative 1, so I take that negative 1 out and I make it minus sign here. So this means that this is indeed equal to 2x sine x 1 over x minus cosine of 1 over x. So after differentiation I got this expression, but that is exactly the function little f of x if x is not equal to 0. So you see that I am assuming that x is not equal to 0. I calculated the derivative of the capital X. I found this one, and then this is exactly equal to f of x if x is not equal to 0. But this is not finished yet, because even though we showed that the derivative of capital F is little f for all x non-zero x's, but we have to show that this is also indeed the case for 0. In other words, I need to also show that f prime at 0, first of all, it exists, and I want to show that this is equal to f of 0. So this is what I want to show. Okay? Okay, let me go to the next page. F of 0, of course, is defined. Little f of 0 is defined, and it is 0. So you see it's here. Okay? But I need to calculate f prime of 0. Because the rule of the function changes when x is equal to 0 and not 0, I will start from the definition of the derivative. So I want to calculate f prime of 0 if possible based on the definition of the derivative. So I need to remember this limit. Limit of f of x minus f of 0 over x minus 0 and send x to 0. If this limit exists, then it means that capital F is differentiable at 0, and the value of this limit is equal to f prime of 0. But that's also very simple, so you can just write the limit instead of capital F of x. I use the first rule. Why? Because when you say x approaches 0, because of the notion of the limit, you know that x is not equal to 0. So this means that I write x squared sine 1 over x, but f of 0 is simply 0, so I don't write it, and in the denominator I have just x, and x goes to 0. And now 1x in the numerator and 1x in the denominator are cancelled, so I get this limit when x goes to 0. Okay, but this limit is equal to 0. Why? Because the limit of the first part when x goes to 0 is 0, and the second function is a bounded function. So it means that for all x which are not equal to 0, the absolute values or sine of x, we can say that sine of 1 over x is between 1 and minus 1. Yes, so this means that the function sine of x is bounded. Okay, so this function is bounded. The limit of the first function is 0, and there is a theorem, which is a consequence of the squeezing theorem in limits, guarantees that this limit is 0. So this limit is indeed equal to 0. So now that this limit exists and is equal to 0, I can conclude that the capital F prime at 0 is 0. On the other hand, we know that little f of 0 is also 0. So this means that I can conclude that f prime of 0 is equal to f of 0. So what I showed is the derivative of the capital F at 0 is equal to little f of 0. And in the previous page I showed that if x is not equal to 0, the derivative of the capital F is equal to little f. So this means that for all real numbers, this is going to be the case. And this means that the capital F defined in this way is indeed an antiderivative of little f of x. Okay, so I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.